Recall the definition of a polynomial. So a polynomial in particular has a degree. So we're going to say a polynomial of degree n. And by this, we mean a function of the form, let me call it p of x, which is equal to a sub 0 plus a sub 1 times x plus a sub 2 times x squared, and so on up to a sub n times x to the n. So it turns out that these constant coefficients of the form a sub k can take on any values. If it's degree n, then a sub n needs to not be 0, but that doesn't have to be true for the other a sub k's here. And if you think about what we like about polynomials, we think of these as kind of a nice class of functions. They're easy to work with, and they're relatively easy to graph. So in some sense, we could think about having a goal now of trying to fit other functions with appropriate polynomials. So in general, suppose I have a function f of x, and it's not a polynomial. It is not, you can't write it in the form I have above. Our goal is going to be that we want to find the polynomial that best approximates this function f of x near some particular point, let's say x equals a, but we'll start with focusing on x equals 0. In a later video, we will generalize what we're finding here to polynomials approximations that are good to approximate f of x near any point of interest. So let's break this up by degree. So we talked about the degree of a polynomial, I should say degree n that I didn't put up here. And so notice that the degree is an indicator there of that highest exponent. And so in this instance, let's focus on coming up with a suitable polynomial approximation where the polynomial that we want to find is of degree n, or 1. So first degree, that's x to the first power. You can think that's going to be a linear function. So we actually have seen this before. So if we want to learn how to approximate f of x by a first degree polynomial that's a good approximation near 0, this is exactly what you do when you find a tangent line. So this is the line tangent to f of x at the point x equals 0. So again, because we're trying to come up with an approximation that is a good one near x equals 0. So we have an equation for that, and in recent times we've been using a certain formula. So let me first of all call it p of x to follow in the theme of our p of x for the polynomial. So if you recall, a tangent line to f at x equals 0 has the property that the slope of that line is f prime of 0, but also that line has to pass through the point 0 f of 0. If I want to represent that line in point slope form, I can do so by expressing it as f of 0 plus f prime of 0 times x minus 0, which is just x. So this, as we've developed before, is a first degree polynomial that approximates f of x near x equals 0. I'd like to point out some facts about this approximation that we're going to keep in mind, especially as we try to find higher degree polynomial approximations. So first of all, notice that p of 0 always equals f of 0. To verify that, plug in x equals 0 to the box expression, and you're going to get p of 0 equals f of 0. Likewise, they have the same derivative at 0, and plugging in 0 is a little bit overkill here. The derivative of this line is the slope, and of course the slope is f prime of 0. So when I take the derivative of this polynomial function, I'm left with just the slope. Certainly then that's going to be a constant derivative, but if I plug in 0, it will likewise give me f prime of 0. Now, this kind of stops here, this theme. If I wanted to find, oops, not the probability. If I wanted to find the second derivative of f, I can't assume that I can get that information from simply knowing this linear function. So the second derivative of the polynomial is 0. I can't assume that that is representative of the second derivative. So perhaps the second derivative is 0 there, we don't know, but this is not an obvious statement. So because the line always yields that second derivative of 0, it doesn't tell me anything about the potential curvature of f. So that's where this approximation tends to not be as good. So what if we want to instead try to think about a second degree? So before I move on to that, again, think about a function like f of x like this. And the tangent line is going to look like this. And so now we can try to imagine instead of a line or a first degree, then what we might want to do instead is come up with a second degree polynomial. The advantage of that is that a second degree polynomial might be able to start to match the curve or the bendiness of f of x. So let's start to consider that. In order to come up with a good second degree approximation, I'm going to try to build off of these notes that I observed about what made the tangent line so nice. So a second degree is we're looking for p of x equals a sub 0 plus a1x plus a2x squared. So the question here is, how do we choose those coefficients with regards to f of x so that this particular second degree polynomial does a nice job of approximating f of x near 0? So based off of our observations above, so meaning with the tangent line, we'll choose those coefficients, so a sub 0, a1, and a2, so that I can satisfy some of the same nice properties of the tangent line. So first of all, let's ensure that p of 0 is equal to f of 0. Whoops. There we go. Let's also make sure that p prime of 0 is equal to f prime of 0. And finally, what we couldn't do with the tangent line, let's match up the second derivatives at 0. So how do we choose the coefficients to make sure that this happens? Well, we come back up to our arbitrary polynomial up here. For this first bullet, I want to plug in x equals 0, and I want to make sure that what I get equals f of 0. If you plug in x equals 0 to this polynomial, you'll be left with a sub 0. So in order to make this true, we need to choose a sub 0 to be f of 0. Now, if p of x is what I have underlined above, p prime of x would be its derivative, which would be a1 plus 2a2x. We want to make sure that when I plug in 0 to p prime of x, what I'm left with is equal to f prime of 0. If you plug in 0 to p prime of x, you'll have a1. So we want to choose a1 to equal the first derivative of f. Notice that the second derivative of this polynomial is simply the constant 2a2. So in order to ensure that the second derivatives match at 0, this says that 2a2 should equal the second derivative of f at 0, or a2 should equal 1/2 the second derivative at 0. So our second degree approximation of f of x is now going to be the polynomial where I'm going to come back up to my underlying polynomial and replace those coefficients with what we found them to equal with respect to f. So this would be f of 0 plus f prime of 0 x plus f double prime over 2 x squared. So notice that if I removed the x squared term, I would have exactly the same polynomial that I found for my first degree approximation. So it appears that as I'm increasing the degree here, I'm building off of earlier polynomials. And of course, we could do this for the third and the fourth, etc. But let's think if we can find a general pattern here for the nth degree polynomial. I'm going to try to emulate what I saw with the second degree. So an nth degree polynomial is, again, like our definition. So just kind of writing out the first several terms and then indicating that this goes up to a sub n x to the n. So we need to choose these coefficients in a way that will make this a good approximation of f of x near 0. So much like I did in the degree 2 case, we're going to choose coefficients so that the polynomial and the function match at 0 for the original function and up through its nth derivative. So thinking of what that looks like, we want p of 0 to equal f of 0. Just like we observed before, if I drop in 0 to my arbitrary polynomial above, that tells me that a sub 0 is equal to f of 0. We want p prime of 0 to equal f prime of 0. And to be clear, maybe I'll put this in a different color. So I have p of x here. Let's think about what p prime of x would be so I can plug in 0. P prime of x would be a1 plus 2a2x plus 3a3x squared, etc. And then the last term would be nan x to the n minus 1. So when I plug in 0 to that, I get a1. And we want to make sure that that equals f prime of 0. Then we want to make sure that the second derivative of p and the second derivative of f match at 0. Again, let's think about what our second derivative of p as a function of x would be. That would be 2a2 plus 6a3x, and so on. And now the last term would be n minus 1, x to the n minus 2. Plugging in 0 leaves 2a sub 2. We want that to equal the second derivative of f. And that means that I should choose a2 to be the second derivative divided by 2. So this is not a surprise. We're finding that up through the second degree here, we get exactly the same thing that we found for the degree 2 polynomial. But what happens as I go further? And so let's consider the next thing, and then I want to try to establish a pattern for what I've seen so far. So we would also like the third derivatives to match. This is something that we could not satisfy with just a second degree polynomial. So thinking about what the third derivative of p would be as a function of x, we would get 6a3, and then this last term would be n minus 1, n minus 2, x to the n minus 3. When I plug in 0 there, I'm left with 6a3. And I want that to equal the third derivative of f at 0. Consequently, I want to choose a3 to be the third derivative divided by 6. So I'd like to be able to extend this to a point where I can ensure that the nth derivative of p at 0 equals the nth derivative of f at 0. And I don't think I've used this notation yet, so just to be clear, when I have the superscript in parentheses, that's a way of identifying that I'm taking the nth derivative. So if I had a 4 in parentheses up there, that would say I'm taking the fourth derivative of the function. We don't typically use this for like first derivative, second derivative, because you can simply put those dashes there. But once I get past the third derivative, it's hard to look at several dashes and try to establish how many there are. So We want this to be true. And in order to see this, I want to get a general pattern. So looking at what I have for these coefficients. So I have a sub 0, I have a1, a2, and a3. It wasn't until we got to a sub 2 that we started to observe that it looked like we had some kind of denominator that we were looking at. So if I want to think about what that pattern is, then let's notice that we could write this as the following. So I have the third derivative of f at 0. 6 is the same thing as 3 factorial. The second derivative is divided by 2, but that's equal to 2 factorial. And I have the first derivative by itself, but you could imagine that the denominator was 1 factorial. And if you remember that we said 0 factorial is in fact defined to be 1, you could write this as f of 0 over 0 factorial. So it looks like the pattern I'm establishing is that I could follow it through and say a sub n would likewise need to be the nth derivative of f at 0 as long as I divide it by n factorial. So this leads to my desired polynomial, and the nth degree here, we actually refer to this as a Taylor polynomial. So now I can define this. We're going to say that the nth degree Taylor polynomial of, or for, you could say, f of x, centered at x equals 0 is defined to be the following. So let me use t sub n. So the n is telling us the degree, t for Taylor, and if I replace my coefficients into this general formula I found for p, that's where I'll get this f of 0 plus f prime of 0 x plus the second derivative at 0 x squared over 2 factorial, etc., up through the nth derivative of f at 0 over n factorial times x to the n. So this whole idea of being centered at x equals 0 is really a reflection of the fact that we're very much focused on properties of f at 0. That's how that's coming into play with those coefficients. Later we'll generalize this formula or this definition for a Taylor polynomial to one in which we can center it at any point that we choose, and we'll see how that's related to this. In the next video, I'm going to look at some examples for how we can actually construct Taylor polynomials for some familiar functions.